So now he's done 6 plus 2 plus 1 is 9. He's got 31 centimetres to go. 2 seconds later, the universe doubles in size again. It's now 80. He would be, if he'd stood still, 18. But he travels another 2 by walking, plus another 1 stretchiness. He's now at point 21. He has got 59 to go. Can you see what's happening? He's never going to make it, because the universe is doubling at such a rate that he's ending up further and further away. 17 centimetres, 31 centimetres, 59 centimetres. The ant's progress is such that he will never ever get to B, because B will always recede away faster than he can move. Let's store that for use later as well. Now we're going to consider what happens in the universe. And for this we need to replace the balloon by the whole universe and replace the ant by a photon of light. Let's suppose that 1 billion years after the Big Bang, there are 2 points which are 100 million light years apart. This is the point where the Earth will be, although it's not there yet, because it hasn't been created yet, and this is maybe a very early galaxy. And a photon of light leaves the galaxy and starts to move towards the Earth. And the photon of light thinks, I've got to travel 100 million light years, and that will take me 100 million years. But of course, that photon will have exactly the same problem as the ant, because the universe is expanding. So as it travels along, it finds that the distance that it has to go continues to expand. And the distance to go continues to be further and further. So although it's making progress at the speed of light, space itself is expanding, and it will take ever longer for the photon to arrive. And eventually, after the photon has made progress, it may at some point arrive at its destination, and that might be 12.7 billion years later. It started when the universe was 1 billion years old, and it arrived today 12.7 billion years later. And the question is, what is now the distance between the Earth and that far-off galaxy? And the answer is 46 billion light years. And so, the radius of the observable universe is not, as you might initially have thought, 13.7 billion light years, but 46 billion light years. And let's just make sure that we understand exactly what we are saying. What we are saying is that if this is the Earth, and that is the far-off galaxy, that galaxy is now 46 billion light years away from Earth. When the photon left it, it was only 100 million light years away. But it is now, today, 46 billion light years away from us. But what we see is the photon that's taken 12.7 billion years to reach us. And we see the galaxy as it was when the photon left it. We see it as it was then. We calculate its distance as to where it is now. There is a possibility that the universe is smaller than the observable universe. You might wonder how that could possibly be the case. And the reason is that light may travel round the universe twice, or even 3 times, or go the long way round. Let me explain what I mean. And for this we need to go back to the surface of our balloon. And let us suppose that there is a point on the balloon which we shall call Earth. And let us suppose that there's another point on the balloon which we shall call a galaxy. Now, light can travel from the galaxy to the Earth this way round the balloon. But of course it can also travel to the Earth by going round the back of the balloon and coming that way. So if we stand on Earth and we look in this direction, we see the galaxy as being that far away. But if we stand on the Earth and we look in this direction, we see the galaxy as being that far away. And we conclude that the galaxy is much further away than it is. It's quite possible that we see two objects in space that we think are two quite different things, but which turn out to be exactly the same thing. And the reason we don't perceive them as being exactly the same is that, of course, it will take the light much less time to travel this distance than it takes the light to travel this distance. And so we will see that galaxy as it was a certain time ago, but we will see it this way as it was much earlier. So the two galaxies, although they are the same, will look completely different because we are seeing them in different points in time. And for that reason, some of the objects which are supposedly out in this region might in fact be the same as objects that are much closer, but because the light has travelled, as it were, the long way round to get to us. Hubble's law tells us that the further away something is, the faster it is travelling. And the question is, at what point is space expanding at the speed of light? Well, Hubble's law tells us that the velocity is Hubble's constant times the distance away. So if we want the velocity to be the velocity of light, which is 3 times 10 to the 8th metres per second, that must equal Hubble's constant, which is 3 times 10 to the minus 18, times the distance. And that gives us a distance of 10 to the 26 metres. We know that a light year is 10 to the 16 metres. So this distance is 10 to the 10 light years, which is 10 billion light years. And that means that any object which is further than 10 billion light years away from us, so let's take an object that's just outside that circle, we will never ever see, because a photon leaving that object will never arrive, because space is expanding faster than the photon can travel. It's a bit like that ant when he was on a balloon that was doubling in size every 2 seconds. His space was expanding faster than he could travel, and consequently he could never reach his destination. And for the same reason, light from this object will never get to Earth, because space is expanding faster than the photon can travel. How then can it be that we can see objects which are 46 billion light years away? The answer is, of course, that when the light left those objects, they were only 100 million light years away. And that's the reason the photon was able to reach us. Light which is leaving an object which is 46 billion light years away today will never reach us. And that means that objects that we can see today, because when the photons left they were much closer, will in due course disappear from view. Indeed, in due course, every galaxy apart from the galaxies immediately close to us will disappear from view forever, because once space has expanded to a point where they are travelling at a speed relative to us of greater than the speed of light, their light will never be able to reach us. Our descendants in billions of years' time will look out at the night sky. They will see the stars in the Milky Way. They may see 1 or 2 neighbouring galaxies, but they will have no idea about any galaxies beyond.